Thank you, April, for the kind introduction, and thank you for organizing this and bringing us together here. So great presentation we have seen prior to this, and just rounding up with another presentation here about the research and investigation we do in Connecticut. So you have seen those pictures, and that's my arm there measuring the deformation of a concrete wall, but this is what you see if the concrete is deteriorated. A lot of cracking, especially those horizontal or map cracking. You have some whitish deposit there near the cracks, and so you can investigate all of this. So we got involved in 2015-16 when we got a call from the Attorney General office in Hartford and the Department of Consumer Protection, and started to investigate what is the cause of those failures which has been seen. Oh, absolutely, yeah. I thought I was too loud. Okay, so we got involved in this 2015-16, and then a report was released. You see there, investigating deterioration of basement walls made of concrete in Connecticut, in a publication 2018. Then in 2019, UCONN provided us with internal funds to start developing a test method to quantify sulfide minerals in concrete, and one publication has led to, you see there, using WD-XRF. And then through the support from our legislature, we then received funds in collaboration then with NIST. And this is our current research. The first part is called the Risk Management of Crumbling Concrete Foundation. So it focuses on continuing developing the test method to accurately test for the presence of pyrrhotite and estimate future damage. And the next phase is the developing of a risk assessment framework. So this is a several-step plan of our current research. So it focuses on the test method, which is the target would be minimally invasive and statistically reliable in terms of sampling and test results. Step 2, they are all interchangeable, is laboratory testing, where we can, under controlled conditions, or the idea is under controlled laboratory conditions, to provide or mix concrete and then test those. This includes also the synthesis of a pyrrhotite as a controlled parameter in our mixes. Step 3 is field testing, so that we can apply our test method and collect, build up a database so that we can compare apples with apples, and all 3 of those steps they merge into a risk assessment framework. In the end, the idea is to have categories like the obvious one, when you see like a cracking is going on and it's almost completely failed, there's no help in doing something else. So often you just need to replace the foundation. But for those cases where you see the conditions are all there, but the deterioration is not there, there might be help in delaying this or pushing the deterioration further out. And we need to know like which homes are affected by this. And currently we are talking about potentially affected 30,000 homes in Connecticut. You have seen the deterioration mechanisms. So definitely like water and oxygen are necessary, and it leads then to all the expansion, but I don't want to go into detail because everyone has covered this already. This is a map from Connecticut showing the veins of pyrrhotite presence, and in this map you have also seen in the previous presentation of the United States. So what can we do in terms of aggregates? So the Canadian research team, they had shown this with using the elemental analyzer for evaluating the amount of total sulfur once the aggregates are crushed and pulverized, so that you have accessible to all sulfur sources there. You can also use in handheld screening WD-XRF tool you see there in the picture to screen the aggregate in the field. So it gives you an idea of the amount of iron or whatever element you're screening for, or sulfur. But it's not as accurate, so it can only be used as a screening tool. And it has currently no implementation to distinguish between sulfate and sulfide sources, which you measure there. In fact, it's calibrated for the sulfate sources, so it gives you some error for the sulfide if you would use this. So that's why only is a screening tool. In terms of looking at aggregates, how reactive they are. You can use, for example, ion chromatography, accelerate your reaction, putting those aggregates in an hydrogen peroxide solution, for example, so having like an oxidizing agent in there. Then sulfates are getting released and you measure the concentration of sulfates. Or with the oxygen consumption method from the University of Laval. So we are also involved in a cross-lab testing with them soon. I hope this is coming. And at UCONN, we have developed some oxidation columns to look at the reaction rate. You can also qualitative measure the presence of pyrrhotite with XRD or using SEM and EDX. You have seen some pictures here prior to this. Those are some examples of using total sulfur analysis using the element analyzer from aggregates we got from the quarry in Connecticut, from the Becker's quarry. This is how, for example, one example looked like, which was unwashed. When you wash it, it changes to this presence of particles. Those are preliminary results. When we crush this, we can also sieve it in different sizes, but we at least attempt number 40 sieve and smaller. If it's above 40 sieve, then we crush it finer. And if you take those fractions and the weights, then you also come up with an average total sulfur amount. And for example, in this case, it's 0.8% or around. The other type of Becker's aggregate we received is this one, where also we crushed it and used the element analyzer with different fractions. Calculating then the average, just the blue bar there, or you take the aggregate, crush it, and you use the material and analyze it as is without fraction it further, and you see like the red bar. And then of course the calculation should be matched closely to each other. But this type of aggregate, for example, contains about, let's say, 0.64% of total sulfur. Then an example of using ion chromatography is shown here, where, as I said, you expose the aggregate to an oxidizing agent. And if you have a control aggregate, you don't see any release of sulfate ions, and so you also cannot measure them. But if you have a pyrrhotite-containing aggregate, especially like we are talking about pyrrhotite being available at the surface so that it can react, then you see an increase in sulfate ion release, and then you could then correlate this to the reactivity of this type of aggregate, or the exposed pyrrhotite from this aggregate. The oxidation column, which is currently set up at UCONN, it uses a system where, do I have the pointer here? Where the material is packed here in a column, and then there is water flowing through the column. There's oxygen being supplied through here. So there is a circulation going on. And then you have the presence of water and oxygen with the pyrrhotite material. There could be containing pyrrhotite, could be pure pyrrhotite, could be synthesized pyrrhotite, whatever you want to investigate. And then you can measure the iron and sulfate release, and then based on this, you can quantify the reaction rate. Using XRD as a qualitative measure, you can use some aggregates. For example, we used aggregate from the Becker's quarry, which were already oxidized, and we scraped off those oxidation products just because it's high in intensity, pulverized this, and then you can see for different, if you use the JADE software to look at the pattern of those intensity peaks, and then you can identify that actually pyrrhotite is present there. Or with those whitish discoloring or deposits near the cracks or at the walls, if you're using XRD, you can determine that there's, for example, Pyrrhotite present, which is a sodium sulfate. So then you could conclude there must be an excessive sulfur source. Either it's internal sulfur or maybe external sulfur coming through the concrete wall, seeping there, and then you have to deposit there. Whatever it is, if you only have this one, it only shows that there's an excess of sulfur or sulfate present. Or you use SEM, EDX to look for what you have heard before, either the pyrrhotite. And you see, for example, here, pyrrhotite are streaks in aggregates. You have also heard of this and seen this. You can look for the elemental composition, look for oxygen and sulfur and iron, and you can see some certain distribution of what's happening there. You can look for the secondary minerals, but you have seen this too here, for example, the adventite. This is just a quick overview what can be done or has been done in the past. The question is then, how do we move from aggregate and how reactive it is, or what kind of amount of sulfur or sulfide we have present in there to then concrete? And you know that aggregate is part of concrete, and usually we don't have any sulfur source in there. But as we know, it might contain pyrite or pyrrhotite and other sulfide minerals. They are so often like metal sulfides. The Portland cement itself contains a sulfur source as well too in form of gypsum, as you know, when it's added during manufacturing. And water usually does not contain any sources, but can then add it to the component if you have external sulfate attack, for example. And then so this all comes together in the concrete, and the question is, what do you have in there? So on average, if you do like take a general mixing proportion of concrete for foundations and the Portland type 1 cement being used and the gypsum content between, let's say, 2.5% to 3%. So all of those assumptions, you come up and make a calculation. It's about an average, and it's not varying, of course, 0.17% in total sulfur as sulfate from Portland cement. So this is kind of your baseline you have in the concrete. And then you have sulfides from unoxidized pyrrhotite, and then you also have a sulfur source from oxidized pyrrhotite, which is then in form of sulfate already in the mix, or further reacted with adrangite. So the idea in terms of risk assessment is what value might most important for the integrity of a foundation or the house structure. And one parameter which comes to the mind or might be important is the compressive strength, right? So if we start off with mixing the concrete, you have a certain compressive strength, and then there's a certain minimum compressive strength, let's say 3000 MPa for foundation wall. And you have certainly over-designed this, but over time, if you have deterioration, you might cross this limit. And then the question then becomes of a concern that in terms of structural integrity of the structure. So what is this time? Would we reach at all the minimum strength or undergo this? You could think of 4 different scenarios. You don't have any pyrrhotite or don't have any deterioration over time. Then we are here scenario 1, everything is okay. And the concrete increases its strength a little bit over time. If you say the deterioration comes from, the pyrrhotite oxidation, but we don't have as much sources in there to lead to deterioration, we might have a decrease, but it levels out and we never reach the minimum. Then you could also say, well, it is still fine. We don't need to be concerned about the structural integrity of the foundation. But if we have too much of sources there, then we might undergo the minimum strength at a certain time. The question would be, when would this be? Or we have so much that the direction will never level out, will never be stable, and it would just deteriorate. So those houses, they would be then at a high risk. And in terms of the reaction rate, so if you want to illustrate this, and if we test for the amount of total sulfur in concrete, we then would test we have this line. But we know we have a baseline coming from the cement in the concrete. We do have potential amount of sulfide, right, from the pyrrhotite-bearing aggregate, and we have sulfates. Now, when we test in the field and take a sample, before I want to say this, over time, the oxidation of pyrrhotite leads to a release of sulfate, as you know. So sulfate increases and the amount of sulfide decreases. Still, the sum would be always the total sulfur. And this depends on alpha as a factor, like how quickly it reacts. But in the field, if we test this, we are at one point in time, for example, this one. And with the test method right now, we can test for total sulfur using the element analyzer. But also if we use WD-XRF, we can distinguish between sulfates and sulfides. So then based on this, we can calculate also the sulfates now contributing to secondary expansion. So this is what then homeowners would get in their report, like different samples have been tested, or removed from the wall or obtained from the wall, tested, and then they get the amount of total sulfur, amount of sulfates, sulfides, and based on the amount of sulfides with stoichiometry, the amount of pyrrhotite presence there. What does this mean? We cannot say, right, because this is research still going on, but we can only say to the homeowners that in comparison to other tests which have been performed at the moment, you are in the lower 10 percentile or lower 50 percentile or higher 90 percentile. So we can place them that they have at least an idea where they are among in comparison to others. As you have heard, the process in general is a long-term process, so we cannot wait 10 plus years to investigate the effects of this reaction. So what parameters would affect when deterioration would develop in the concrete. So somehow this needs to be connected, accelerated test methods with then deterioration in the field. Distinction between sulfates and sulfide is one important step we feel to make an accurate prediction. So in the laboratory test, as I said, we can control all the parameters and also have certain steps included to accelerate those reactions, and the collection of field data over time is needed to develop the database. So far, we have 90 plus foundations being tested. This includes foundation replacements. It also includes foundations like the walls from homeowners, where we used a vacuum drill to obtain the material. COVID had an issue because for a period of time, we couldn't then move or schedule an appointment with the homeowners, but now it's getting better. And if there's no help or anymore, then the foundation needs to be replaced. You might have seen those, so entire houses or several condos are being lifted, foundations being replaced. So when the foundations were being replaced, then we also had some access to those materials. There is a website available where every person in Connecticut and Massachusetts, they can go to, they can also inform themselves, but also can provide their data, and we then come out and test for free and then get this report. We target 5 holes or drill 5 samples from each foundation. They are 1 inch in diameter, about 5 inches deep. So we leave some concrete. We don't drill through the water penetrating layer outside. We don't use any water, and about 60 minutes, and then we are done out of the homes. Again, it will be patched as you see there. So not more than 60 minutes, and then we are done there. We can drill more holes. It's not a problem. We can analyze more just based on statistical variation and analysis. We have found that 5 holes is sufficient for those homeowners to evaluate the presence of pyrrhotite or not. With those foundation samples you see here, then we can use those to drill several times. Those are the 1 inch diameter holes you see here, and then we can analyze statistical variations within 1 sample and so on. And this is how it looks in the field. And then this powder collected with a vacuum drill gets then brought back to the lab, analyzed, and further prepared if we need to crush it finer, for example, and analyzed. So far, we have done over 1,000 tests in terms of total sulfur and over 1,000 tests in terms of WD-XRF investigation. And then with this database, you can then start categorizing certain phenomena or certain conditions in the field. For example, foundation has been replaced or they show cracks more than 1 millimeter, then the total sulfur works. For example, the average here with them standard variation, or if the foundation was not replaced smaller than 1 millimeter, then the total sulfur currently measured in this, and so on, or no cracking observed, pyrrhotite detected is here. So it gives you a kind of a sense where when there would be critical limit for reaching a deterioration which needs replacement of their houses. So this is being done, is continued to being done, and it needs to be done over the next years as well too, because it's a time-consuming process to get those samples and analyzing them in the lab. Related to, so besides total sulfur measurement, we use the WD-XRF measurement, then to distinguish between sulfates and sulfide. And if you do this, you use WD-XRF, you get like different intensities, and those are at a specific angle for the sulfide or sulfate species. And for example, the peak here, which we define as K alpha, and this peak here, K beta, and the satellite, K beta prime here, those are indicative of the presence of sulfates and sulfides. So for example, the ratio between K beta and K alpha gives you the quantity, gives you a means to quantifying sulfates, sorry, and between the satellite K beta prime and K beta gives you means of quantifying sulfides. In conjunction with total sulfur, then you can calculate the absolute amount of those species in the aggregate or in the concrete. And it also, if you know then you could also calculate or evaluate the reaction progress. So for example, if we have just one level of set in this time-dependent behavior from the field, then, for example, you know the total sulfur from the concrete elemental analyzer, you subtract the baseline of the Portland cement, so then you get the total sulfur coming from the aggregate. So this would be, if you have the total sulfur here, subtract the baseline from sulfates, then you have like this difference only from here to here. And then with the WD-XRF, you know then the total sulfates, so it's like this amount, and like this point, you subtract the Portland cement baseline from this, so then you have this little red arrow. And if you take this little red arrow, so like this value, divide this by the total sulfur coming from the aggregate, like so this little red arrow divided by from the difference between here, then you have an idea what the oxidation reaction progress is. In terms of the WD-XRF, there's a whole calibration method development behind this, and it always needs to be fine-tuned further. But in the end, what you can see, you have certain calibration curves indicating sulfide to total sulfur ratios, sulfate to total sulfur ratios. Also, we have a curve for sulfide over total sulfur ratios. But the goal is, in general, is to standardize in the end sampling and test method to test for sulfides and sulfates. We also do damage evaluation, so using regular traditional crack measuring tools, so for crack width and crack length. And then also we explore resonance frequency and surface resistivity to evaluate the damage inside the concrete non-destructively. And then, of course, we do in our lab expansion tests where we use the mortar test. The acceleration steps at the moment, we aimed at increase the purity, increase the reaction area in terms of particle size, and increase the possibility of transporting the iron, so having a porous structure. With the expansion, you want to isolate shrinkage and oxidation and formation of aggregate or tormosite under different environmental conditions. One part I wanted to show you here is the acceleration using more pure or purer pyrrhotite. 3 different avenues can be pursued, or we have pursued. One is synthesizing pyrrhotite following the Professor Paul's method from the University of UK Reading. And you see here in a quartz tube, like how pyrrhotite has been synthesized. So it's 100% of pyrrhotite. You can decompose or use the decomposition of pyrite to pyrrhotite. So pyrite you can buy. That's not an issue. So buying pyrrhotite is an issue. You can, it's not easily accessible. But you can buy a pyrite, and with a certain temperature regime, you can convert this into pyrrhotite. And also using our aggregates from the Becker's quarry, you can use magnetic separation to ground this, and you see a magnet here, still the pyrrhotite connecting or infused particles adhere to this, and then you can increase the total sulfur, for example, to 9%. We were able to, and then if we then use this in concrete, it accelerates the reaction As a last slide here, there's a lot of communication and support also going on, and I want to have a big shout out and express my gratitude and thanks to all the entities involved in this. This is NIST, the National Stone, Sand and Gravel Association, Connecticut Foundation Solutions, Indemnity Company, Croc, homeowners when we are in contact with them, different contractors for foundation replacement. There are a lot of citizen advocacy groups, and major ones are the ones in Connecticut, Massachusetts, and contact with the one in Ireland, which led to the European Parliament as well too. In media, those topics is being covered. Connecticut Innovation, different companies, Congressman Joe Courtney and legislature, thanks to them. Different research group, Laval University, Penn State University, Trinity College, the University of Reading, UK, Professor Powell there, and also University in North Ireland. Also in contact with our state geologist, Margaret Thomas, different petrographers, and ACI here in different committees. So thank you to all of them. Thanks.